Hello, my name is Dillon Maltese, and today I'm going to be talking to you about my voice-controlled robotic arm for assisting complex surgical tasks. In the US, over 250,000 people die from medical errors each year, and of this, over 4,000 people die from surgical errors yearly. What labs like mine have done are implement augmented reality into the operating room in order to try and combat this issue. This is great as it allows the surgeon to see the patient's anatomy in real time, but it does come with problems. The main is that the surgeon needs to operate an ultrasound probe on the patient at all times in order for the headset to actually update. So this is obviously a problem as the surgeon only has two hands and he needs both of them to operate. So what I have set out to do is create a voice-controlled robotic arm in order to act as the surgeon's third arm and assist him with this task. So my engineering goal for this project was to actually develop and create this third arm and then to make it voice controlled because this will allow for it to actually be a surgeon's third arm. And it should also be able to manipulate ultrasound probes properly, which will in turn allow for augmented reality to be able to be implemented into the operating room and reduce the stress on a surgeon. So now going into the design, it all started with just some sketches. So I was in the operating room with my lab when I saw this problem happening. And my first sketch, as you can see on the picture on the right, was kind of my way of trying to solve this problem. This led into me proposing it uh to my lab and the head of my lab. And he was very skeptical at first. He didn't really think I could do this, but he said, you know what, we'll give you the time and space to do it. And if this really does develop, then we'll start giving you more and more supplies in order to make this into a product. This is when I started 3D modeling and chose hard plastic as my material for this project. The main reason was because I was fortunate enough through Weill Cornell to have access to a 3D printer, which allowed for quick iteration. And on top of this, hard plastic is very lightweight and sturdy, which is great for something in the operating room. This is when I also chose to use NEMA 23 stepper motors with two-stage epicyclic gearboxes. And now to kind of go more into what a gearbox is, it's this attachment to a motor that allows for this thing called a reduction ratio. And what I mean by a reduction ratio is decreased speed, but increased torque. So more weight can be pulled by the motor. This is great for something like an arm in the operating room because you need it to be able to pull more weight than necessary in order to make sure it doesn't break down in the operating room, which would be pretty bad. And now to go into a little more on how this works. So you start with the motor down here, which then connects to this sun gear, which is this gear right in the middle. When the motor spins, the gear spins, and it spins the three planetary gears on the outside around this stationary ring gear. These three planetary gears are rotating at the decreased speed from the reduction ratio and are connected to the output shaft. The output shaft then screws into the second sun gear, which becomes the input for the second gear set, and the second output shaft is the final output. The reason I chose to use two stages for this is mainly because the reduction ratios are multiplied. So what I mean by that is if the first gear set has a 5-to-1 reduction ratio and the second gear set also has a 5-to-1 reduction ratio, the total reduction ratio is 25-to-1, which is pretty big. So now going more into the calculations, the main thing I want to emphasize here is the fact that the teeth are what matter. So what I mean by this is these ridges right here on the gears are the teeth, and the amount of teeth on each piece is what determines the reduction ratio because that's what determines how fast the planetary gears actually rotate around the whole ring gear, which is why the size doesn't actually matter. It's mainly the teeth. So now to go into the base and first arm, the base uses a 1-to-25 reduction ratio. And this is the biggest reduction ratio on the arm because if you look at the full diagram, you can see here is the base. So it is rotating the most weight out of anything else on the arm, which is why it needs the highest reduction ratio because it's trying to pull the most weight. So the way this works is the output shaft or the final output is right here and it screws into these two pieces right here. And what these two pieces are these shoulder to base connectors. So the way they work is these four screws on the bottom screw into the final output shaft of the base gearbox. And then uh, both of these fit snugly onto each side of the shoulders gearbox. And you can kind of see right here that the shoulder gearbox is right in the middle. It's this white piece in between. And the shoulder gearbox's motor is right over here on the right, sticking out of the back. And the way I connect the shoulder gearbox to the first arm is by using these five screws that screw through the first piece of the arm into the shoulders gearbox. And if you look closely here, you can also see the first part of the arm is actually split into two pieces. And the reason for that is because the 3D printer I had access to was 10 inches by 10 inches by 10 inches. And the whole first piece of the arm is 16 inches long, meaning that it wasn't possible for me to print it all in one print. So what I did was I printed these small little squares that screw into both sides of the first piece of the arm in order to connect them together and make sure that I could get this 16-inch long arm without needing to use a different 3D printer or use a different workaround. And to now go into the second arm, it's very similar to the first arm. It uses a 1:15 reduction ratio, again, climbing up as you go further up the arm. And it's seen right here. That's the gearbox. So there's a NEMA 23 stepper motor inside the top of the first arm that becomes the input for the gearbox. And then it screws in just like with the first arm right here to the second arm. And this piece right here is kind of like the shoulder to base connector, except it connects the uh, furthest point of the second gearbox to the first arm and then allows it to rotate. And again, so this piece is actually 13 inches long, which again is too big for the 3D printer I had access to, which is why I split it into two, just like with the piece before. So now going into the wrist and claw joint. So the way the wrist works is it connects to a NEMA 17 stepper motor, which is seen right here on the second piece of the arm. And the output shaft from the NEMA 17 stepper motor fits right into this circular hole on the wrist here. And the way it works is that when the NEMA 17 stepper motor rotates, the wrist rotates with it, in turn being able to move where the claw is facing. And so, as you can see, I kind of made this odd looking semicircle shape on the top of the wrist. And the reason for that is because if you look at the second piece of the arm, it's also curved. And so what this semicircle hole allows me to do is it allows the whole wrist to rotate full 90 degrees in each direction without ever coming in contact with the second piece of the arm. And this is crucial because you can't have two things coming in contact with each other frequently, as they'll eventually deteriorate and lessen the lifespan on this arm, which is not what we want. We want it in pristine condition because it's performing surgery. It needs to be very accurate. This is also, as you can see at the top of the wrist, there's this hole here, and that's to hold an MG996R servo, which is used to rotate the direction of the claw. And so currently the claw is in progress and it's in the works. And the what I'm doing is I'm 3D modeling this piece up here called a rack and pinion, which will allow the claw to actually open and close and clamp onto an ultrasound probe properly and hold it properly. So now going into the calculations I did for seeing how far the arm could reach in each direction, I used trigonometry here, so sine and cosine. And the way I did this was I labeled the joints, as you can see here. Those are where the stepper motors are located. And so this joint, and using these stepper motors and this joint, I found out depending on what angle the stepper motor is rotated to, how far in each direction is the arm actually pointing. And this was crucial in the earlier stages of prototyping and designing this arm, as it allowed me to figure out how big I really needed each piece to be in order to work with all patients. Because again, this arm is used in the operating room. It needs to be adaptable and it needs to be used for different types of patient, different patient sizes, whatever is
Minute
required.
warning.
And so now going into the motion and control system, I'm happy to go into this more in depth later if you have any questions. But the basics of how it works is it uses a NEMA 23 stepper motor like before, which plugs into a TB6600 stepper motor driver and is powered by 12 volts and 5 amps. And so this Arduino code right here is the basic code of how I controlled a NEMA 23 stepper motor. And now going into the voice control aspect, right here you can see is some Python code that I used. And this is how I used the voice commands on the actual robot. And so I was able to say, robot, do this, and it looked for that keyword and execute that. So now going into the testing and results, uh, tests have been started to be conducted on this joint movement accuracy and speed, and the arm is moving very smoothly without vibrations, and the voice control system is successfully interpreting. So now I just want to play a little video. And so here I say robot move, and as you can see, it moves properly. This was actually taken in my dining room and was the first time I tested it, so I was very happy it worked. And so now going into the final future work and conclusions. So the future work again is to finishing designing that claw, and then I'm taking this to the SAIL lab, which is my neighboring lab at Weill Cornell, and this it uses these surgical environments to mimic a surgery, and this is where I'll be testing all of these different uh, pieces and making sure everything works. And to kind of put into the grand scheme of things is my final piece. This robot, again, it'll allow augmented reality to be seamlessly integrated into the operating room, which will allow for a surgeon to kind of be able to use augmented reality and hopefully reduce those staggering numbers from the start. And with
That's
that, I open it up to questions.
that's time.